Can you hear me good? Okay, cool. Let's start. Use this. Okay. All right, so last week we talked about k-means or center-based clustering methods. Okay, we talked about for k-means, how do we calculate the center of a cluster? Okay, and let's move a little bit back to Okay, so we talked about the k-center clustering. We talked about k-median clustering, and for k-median clustering, how do we calculate the center of a cluster, and which distance measure that we should use, and similarly for k-means, which distance measure we should use, and how do we calculate the center of a cluster. And we also introduced two different algorithms for k-means. The first one is Lloyd's. The second is what we call a Ward algorithm. Okay. And then we talk a little bit about spectral clustering. Before we talk about spectral clustering, we need to introduce similarity graph. Okay. So for similarity graph, we covered the definition of a degree matrix D. Okay, the degree for a vertex on graph G is the sum of the weights linking to the node or linking to the vertex Vi. Okay, and we introduced the definition of indicator vector. Okay, all right. And we introduced three different ways to calculate the weights between two vertices on graph G. Okay, the first is called the epsilon neighborhood graph, which is based on the distance of two vertices. Okay, the second is k nearest neighbor graph, and the third is the fully connected graph. Okay, now let's move on to talk about spectral graph theory. Okay, so we have given a definition about the diagonal matrix D before. Okay, so diagonal matrix D is based on the degree of each vertices on graph G. Okay, and we give our another definition here, which is called a graph Laplacian matrix L. Okay, so L is defined as matrix D minus matrix W. Okay, so D, as we know, is a diagonal matrix, the degree matrix, and W is the weight of each edge on graph G. Okay. It is very easy to prove that matrix L is symmetric and it doesn't depend on WII. Okay, why the Laplacian matrix doesn't depend on WII? Because we can take a look at the element LII here. Okay, so LII is equal to DII minus WII. Okay, and according to the definition, DRI is the degree DI of node VI. Okay, so the degree DI is equal to the sum, this sum. Okay, sum J from 1 to n, Wij minus Wii. Okay, so we see here in this surmount, we have WII. So WII minus this WII. That's why we say the Laplacian matrix L does not depend on WII. Okay, and later we will see that the Laplacian matrix L is positive semi-definite. Okay, so the definition of a matrix to be positive semi-definite is for all vectors F. Okay, we have F transpose times matrix M times F is greater than or equal to 0. This is the definition of positive semi-definite. Okay. And from linear algebra, we know that a symmetric graph is positive semi-definite if and only if, okay, if and only if all of its eigenvalues are real and non-negative. Okay. Now we will see that the graph Laplacian matrix L is positive semi-definite, and we will take a look at into one of its spatial eigenvector and the corresponding, eigenvalue and the corresponding eigenvectors. Okay, so we move on to this theorem. And the theorem gives us 3 results here. Okay, so for the Laplacian matrix L, it has the following 3 properties. Okay, first for every vector F, okay, and then F transpose times L times F is given by this expression. Okay, and the second property is that L, okay, matrix L is symmetric positive semi-definite matrix. Okay, the third property is that the smallest eigenvalue of L is 0, and its corresponding eigenvector is the indicator vector 1. Okay, with all element values 1. Okay, so before we prove this theorem, we can take a look at these 3 properties. Okay, so the first one, the first property, F transpose LF is equal to half and this amount. So we can take a look at this amount. It is Wij, okay, Wij times the square of Fi minus Fj. Okay, so as we know, for all of the weights or the similarities on the on graph G, Wij is non-negative, right? And Fi minus Fj square is also non-negative. Okay, so actually we can, from property 1, we can see that F transpose L times F, the whole expression itself is non-negative. Okay, so if we can prove property 1, we can directly get the result for property 2. Okay, we can see that L is positive semi-definite. Okay, and again, according to linear algebra, okay, if so for a symmetric graph, if it is symmetric matrix, if it is a positive semi-definite, which means all of its eigenvalues are real and non-negative. Okay, non-negative. So from the last property, we can see that for matrix L, it does exist eigenvalue, which is equal to 0. Okay, and we can get a very spatial eigenvector for the corresponding eigenvalue, which is the index vector 1. Okay, so those properties are very important. Now let's take a look at the proof of this theorem. Okay, for property 1, F transpose times L times F. Okay, according to the definition, L is G minus W. Okay, and then we can rewrite this expression by using the element-wise, the elements in each of the vectors and matrices. Okay, so first, as we can see, okay, so for matrix D, it is diagonal matrix. Okay, with the diagonal elements equal to Di. Okay, and W for matrix W, it is that the elements are Wij. Okay, and then for this expression, okay, all right. So for expression, let's say for the first part, okay, as we know, Di is equal to sigma j Wij, right? So Di is equal to this amount. Okay, now if we take half out of the whole expression, okay, and then we will get 2 Di's or 2 sigma. Oops, this should be, yeah, never mind. 2 sigma j. Okay, 2 sigma j Wij. Okay, and now if we take a look at this expression, we will see that if we move sigma I and sigma j Wij, okay, if we move this part out, we will get Fi squared minus 2 Fi Fj plus Fj squared, right? So this is exactly the square of Fi minus Fj. Okay, so this is exactly the result of the first property. All right, so the first property is done. Now let's move on to second property. Okay, so according to the result of the first property, we get F transpose LF is equal to this expression. As we said, Wij is non-negative. Okay, and then F transpose LF is also non-negative. So which proves that the matrix L is positive semi-definite. Okay, so this is the second property. For the third property, so it is said that the smallest eigenvalue of L is 0. Okay, so what do? We just need to prove that 0 is an eigenvalue of L, and the index vector 1 is a corresponding eigenvector. Okay, so we simply use matrix L to times or to multiply the indivector, the indicator vector 1. Okay, so L times 1 is equal to D times 1 minus W times 1. Okay, and it's very easy to prove that D times the vector 1 is equal to Di. Okay, and similarly, W times vector 1 is also equal to Di. Okay, so then we get this result. So L times vector 1 is equal to vector 0. Okay, vector 0. And vector 0 is equal to 0 times vector 1. Okay, so we can see that 0 is an eigenvalue of matrix L, and 1 is the corresponding eigenvector for L. Okay, so this proves that 0 is the smallest eigenvalue of L, and 1, the vector 1 is the corresponding eigenvector. Guys, do you have any question here? Okay, I take that as a no. Actually, this is very easy to prove that L times 1, D times 1 is equal to DI, and W times 1 is equal to DI. It's very easy to prove, so I'll just skip it. Right, so this proves our theorem. Okay, and then move on. We will first have a look at 2 definitions. You might have heard of these definitions before. Okay, so given us a matrix, a square matrix M, okay, and eigenvalue lambda of this matrix will have these 2 definitions, okay, or these 2 multiplicities. Okay. The first is called algebraic multiplicity. Okay, so if we have a matrix M and lambda is one of the eigenvalues of M, and then M, or for matrix M, it has algebraic multiplicity K. If the characteristic polynomial P and X has a form, P and X is equal to X minus lambda to the power of K. See, okay, the multiplicity is K, means for the polynomial P and X, it has this expression, X minus lambda to the power of K. Okay. You may wonder, what is the polynomial P and X? Okay, so P and X, as I have written here, okay, so P and X is equal to the determinant of matrix M minus lambda times matrix IM. Okay. Guys, do you have any question about this definition? Okay, you might have or learned this definition before. Okay, so the second multiplicity is called geometric multiplicity. Okay, the geometric multiplicity K, if lambda has K linearly independent eigenvectors. So the second definition is very easy to understand. So for this eigenvalue lambda, if it has K linearly independent eigenvectors, and then we say K is the geometric multiplicity. Okay. We will use these 2 definitions in the next theorem. Okay, and from this theorem, you will see how we develop the spectral clustering. All right, so this theorem, let G be an undirected weighted graph, okay, with non-negative weights. So which means Wij are non-negative, okay, and which, so for this undirected weighted graph, it has exactly K connected components, okay, from A1 to AK. Okay, so given us this graph, it has K connected components, and then the algebraic and geometric multiplicities of the eigenvalue 0 of the Laplacian matrix L are both equal to K. Okay, notice that this K is the number of connected components. Okay, so the algebraic and geometric multiplicities are all equal, both of them are equal to K, and K is the number of connected components. Okay, and the eigenspace of eigenvalue 0 is spanned by the indicator vectors. Okay, this is 1 at component A1 till 1 at component AK. All right. So we can take a, before we prove this theorem, we can take a look at the result of this theorem. Okay, so given us undirected weighted graph, the graph can be fully connected, or it may have several or multiple connected components. Okay, so assume it has K connected components. So this K, oops. Okay, sorry about that. So we see that K is greater than or equal to 1, so which means one component, okay, or less than or equal to, let's say, n. Let's say graph G has n vertices. Okay, so if K is equal to 1, which means G is, so all of the nodes are connected on graph G. If K is equal to n, so which means there's no edge on graph G. All right. Okay, so given us this graph, and then the first result is the algebraic and geometrical multiplicities of the eigenvalue 0 of the corresponding Laplacian matrix L are both equal to K. Okay, K is the number of connected components. All right, and the eigenspace of the eigenvalue 0 is spanned by the indicator vectors 1A1 till 1AK. All right, now let's move on to the proof of this theorem. Okay, so the first step of this theorem, of this proof, is to assume the graph is connected. So which means we assume K is equal to 1. All right, we assume K is equal to 1. Okay, so which means it has exactly one connected component, right? And we let F be an eigenvector. Okay, all right. If we make this assumption, then we need to prove this and the eigenspace, right? Okay, so now we let F be an eigenvector with eigenvalue 0. Okay, and then we will have L times F is equal to 0 times F. 0 is corresponding eigenvalue. Okay, and then this is equal to 0 vector. Okay, so according to this, we will get F transpose LF is equal to 0. Okay, and then according to previous theorem, we will have this amount equal to 0, right? Okay. Okay, and then from this equation, we will see that we will prove that for vector F, F, all of the coordinates or the elements in F are constant. Okay, and then we can prove that the indicator 1V is an eigenvector of L corresponding to eigenvalue 0. Okay, and how do we prove it? Okay, now, if two vertices Vi and Vj are connected by an edge, and then we will have the corresponding weight for edge ij is positive. Okay, so if wij is positive, which means this part has to be 0. Okay, so which means fi is equal to fj. All right, so, but this is just for one edge. Okay, if have an edge linking Vi and Vj. Okay, now we can move from an edge to a path, to any path on the graph, on the undirected weighted graph G. Okay, so going along any path, okay, so how should I write it? So for an arbitrary edge, we can prove Fi has to be equal to Fj. Now, actually, we can rewrite this to get something like, or to prove this, we just need to prove that. So for an arbitrary path, let's use sigma to represent a path. Okay, for an arbitrary path, and then arbitrary two arbitrary nodes, let's say, Vi and Vj are on this path. Okay, on this path. We just need to prove that Wij and then Fi minus Fj square is equal to 0. Okay, so if this is equal to 0, and then we can easily get that this is also equal to 0, right? Okay, so now, so from here we can get for arbitrary edge, we get Fi is equal to Fj. Now for an arbitrary path, or any two nodes on the arbitrary path, we also have this amount equal to 0. Okay, so if we can, after we get this, we will see that actually for any two nodes Vi and Vj, okay, in graph G, we will have Fi is equal to Fj. Okay, so for any two nodes Vi and Vj, we will have Fi equal to Fj. Okay, so which means in the vector F, okay, for the vector F, all of the coordinates must be constant. Okay, so we have F1 equal to F2 equal to Fn. Okay, so we can conclude that yes, the indicator vector 1v is an eigenvector of Laplacian matrix L corresponding to the eigenvector 0. Guys, any question here? Right. Okay, guys, you can also find the full proof from the textbook. Right. So this is under the condition of the graph is connected, okay, which means it has only one connected component, or k equals 1. All right, now assume that the graph G has k connected components, or k is greater than 1. Okay, and then without the loss of generality, we assume that the vertices of the connected components are listed in order of the component they belong to. Okay, then the original matrix W can be written as a block of matrix in this form. Okay, so W1, the block, the first block W1 corresponding to the first connected component A1, and W2 corresponding to A2, WK corresponding to the component AK, right? So according to the definition of Laplacian matrix L, we can also get a similar block structure for matrix L. Okay, so we get L is equal to L1, L2, Lk, okay, corresponding to the K components. All right. And then we see that for each component, okay, for each component, or for each block matrix Li, okay, so for each block matrix Li, we have Li has only one component, right? And we have proved that if K is 1, or if the graph is connected, and then we have the result that okay, for the eigenvalue 0, it has a corresponding eigenvector, which is the indicator vector LAI. Okay, so we have proved that for each matrix block Li, because the corresponding component is connected, so we have that for the eigenvalue 0, it has the corresponding eigenvector 1 AI. Okay, so we see here, because each Li corresponds to a single connected component, so it has 0 as the smallest eigenvalue with an eigenvector LAI. Okay, so consequently, the matrix L, okay, the full matrix L has as many eigenvalues 0 as there are connected components, and the corresponding eigenvectors are the indicator vectors of the connected components. Okay, guys, do you have any question here? Okay, we got a question. Are W1, W2, WK square matrices of correct? Yeah, because each Wi corresponding to the corresponding to the corresponding component. Each component may have different components may have different number of nodes in it, right? So there are square matrices with different sizes. Correct. Any other questions? Okay, let's move on. right, so we've proved the second theorem. Okay, we have another question. So we are just saying that the kernel of L is k-dimensional. What do you define the kernel of K? I can imagine your definition of kernel, but okay, the vector space formed by the set of vectors mapped into the non-vector space under a linear map. Yeah, you can say that. Okay, Felix. So the eigenvectors we are talking about corresponding to eigenvalue 0. Okay, we may also have other eigenvalues, some other positive eigenvalues, and for those these eigenvalues, they also have the corresponding eigenvectors. Okay, so the vector space you're talking about here, corresponding to the eigenspace of eigenvalue 0. Okay, and in this case, yes, you're right. The kernel, I can't say the kernel of L, the kernel of the eigenspace of eigenvalue 0 for matrix L is k-dimensional. Does that answer your question, Felix? Okay, cool, thanks. All right, okay, let's move on. And then according to the above theorem about the eigenvectors corresponding to the eigenvalue 0, we can use this theorem to find connected components of graph G, okay, to find the connected components. Okay, how do we find connected components? All right, let's talk about this points one by one. Okay, so assume now we have a graph G which has k-connected components. Okay, and we would like to find all of the components, all of the connected components of G. Okay, and after we form the Laplacian matrix L, we can use some standard software to find all of its eigenvalues, including the eigenvectors for eigenvalue 0. Okay, but the thing is, okay, however, generally these eigenvectors would not be the indicators 1ai. Okay, because okay, sorry, I moved too quickly. Wouldn't it be the indicators 1ai of the connected components, but it will output k mutually orthogonal linear combinations of these indicator vectors. Okay, because any k orthogonal vectors in the eigen subspace corresponding to the eigenvalue 0 are equally good candidates. Okay, now assume the software we're going to use output k vectors or k eigenvectors. Okay, and we denote them as E1, E2 till EK. Okay, as we emphasized here, for each eigenvector EI, there are linear combinations of the indicator vectors. Okay, so for example, E1 is the linear combination of 1 one A1, one A2, and one AK with corresponding coefficients. Okay, right. So as we, I forgot that student's name, pointed out, as Simon pointed out, that for each AI, different AIs have different dimensions or different size. Okay, so I explicitly write vector E1 here. Okay, so E1 is equal to, okay, corresponding to the indicator vector A1. Okay, so E1 is alpha 1, 1, alpha 1, 1. We don't, there could be one or multiple alpha 1, 1s here. Okay, so we have a list of, or block of alpha 1, 1. And similarly, we have a block of alpha 1, alpha 2, 1. Okay, a block of alpha 2, 1. And the size of this block corresponding to the size of A2, okay, until we reach to 1 AK. So it is from alpha K1, okay, alpha K1, the block of alpha K1s, and the size of the block corresponding to the size of AK. Okay, and notice that the dimension of E1 or EI is n times 1. Okay. So this is about the eigenvectors that you may get from a software. Okay. Now we can form up a matrix E. Okay, we can form a matrix E of size n times k. Okay, because we have k eigenvectors E1 to EK. Okay, so we can form a matrix E of size n times k, whose k columns are the eigenvectors EI. Okay, so we have, so let's say this is E1, E2, EK. Okay, is this correct? Hang on. Yeah, that's right. All right. Okay. So this is about matrix E. So matrix E with columns are the eigenvectors EI, and now we consider n vectors yi, which are the rows of matrix E. Okay, so this is y1, y2. Sorry, this is not. I can't say y2. Okay. Let me explain a little bit more about matrix E. Okay. So in matrix E, each column corresponding to eigenvector EI. Okay, so here we have E1, E2, EK. All right. As I have explicitly write E1 here, so we can put this vector or the explicitly expression of E1 here. So E1 is alpha 1, 1, a block of alpha 1, 1s till a block of alpha K1s. All right. And similarly for E2, we have a block of alpha 1, 2 till a block of alpha K2. Okay. Now, if we focus on the rows, okay, the rows of the rows in matrix E. So let's say we have, for the first row, we have Y1, okay, and this we would have Y. Tell me what is the index of this row? Any idea? Not Y1 anymore. So this is a row number 1, and this is a row number A1, right? So because these corresponding to block 1, and as we said here, look at here, the size of this block is A1, right? So, oops. Okay, so this is Y1, and then we have dot, dot, dot. For this row, we have YA1, right? And dot, 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 till the last row, we have YN, right? Any question here? Okay, let's move on. Yeah, I understand could be a little bit tricky here. Okay, so now for every two vertices Vi and Vj, if they belong to the same connected component, let's say Am. Okay, so which means they are connected in component Am. Okay, and then the corresponding vectors Yi and Yj are identical. Why they're identical? Okay, now let's say if they belong to component A1, okay, if they belong to component A1, which means here, component A1, okay? So if they belong to component A1, and then we see that for arbitrary vertices Vi and Vj, and then the corresponding vectors Yi and Yj, they are identical, right? So let's say if Vi is corresponding to V1 and Vj corresponding to Va1, and then these two vectors Y1 and Ya1, they're the same, right? Okay. Guys, any question? Okay, cool. Thanks. Let's move on. Da, da, da. Okay. That's very good. Okay, so according to these property, this will allow us to easily identify the connected components by selecting points I, with identical corresponding vectors Vi. Does that make sense? So we can easily identify the connected components. Okay, so after we use a software to get the eigenvectors for the eigenvalue 0, okay, we can construct, by using these eigenvectors, we can construct a matrix E, okay? And then from this matrix E, we can easily identify the components, because if any two vertices, they are in the same component, and then the corresponding Y vectors, the row vectors are identical. So from here, we can easily get the components of graph G, right? Okay, what am I doing? Okay, so this is about finding out the components of graph G. Now let's move on to spectral clustering. Okay. All right. Let's talk about these points one by one. So first, when we cluster points into disjoint clusters, okay, so we are talking about unoverlapped clustering. In the future, you may also have, or you may also read papers about, overlapping clusters. Okay, but in today's class, we only focus on unoverlapped clustering or disjoint clusters. Okay, so when we cluster points into disjoint clusters, we want any two vertices Vi and Vj with high similarities to be in the same cluster. And any two vertices from different clusters are either not to be connected with an edge or to be connected with an edge with a very small weight. Okay, so which is what we called last week. We maximize the similarity for the nodes within clusters, but for interclusters, we try to minimize the similarity. Okay, we maximize the inter-similarity and minimize the inter-similarity, right? Okay, let's move on to the second point. Second point, the clusters should be, in a sense, approximate components of tightly connected vertices, okay, with weak edges between such unapproximate components. Hang on. Sorry, between, yeah, you're right. I was wrong. Yeah, between these approximate components. Okay, now, if we take k eigenvectors E1 to Ek corresponding to the k smallest eigenvalues, okay, in place of eigenvalue 0 of multiplicity k, okay, instead of the k eigenvectors corresponding to eigenvalue 0, we choose the k smallest eigenvalues to approximate eigenvalue 0. Okay, all right, we take these eigenvectors and form the corresponding matrix E with the eigenvectors as the columns. Okay, and then again we consider the row vectors y1, y2 till yn. Okay, if the graph G had connected components, and then for every 2 points, Vi and Vj from the same component, we saw the corresponding vectors yi and yj would be identical. Okay, but for clustering, okay, this is still about connected components. Okay, components are different from clusters, right? So for clustering, these is no longer this case, which means is no longer the connected components. Okay, but since within each optimal cluster, the weights of H are high and the weight of H between different clusters are low. Okay, so so we can hope that take a look at this highlighted part. We can hope that the points Vi and Vj from the same optimal cluster will have similar vectors yi and yj, and points Vi and Vj from different optimal clusters will have substantially different vectors yi and yj. Okay, so the spectral clustering is based on finding out connected components of graph G. Okay. All right. So bear this in mind. We will use this for spectral clustering. Okay. So this heuristic analysis suggests this spectral clustering algorithm. We'll take a look at the detail of this algorithm. Okay. So the input, similar to k-means, the input is a set of data points A. A is from A1 to AN. And we also need another input, which is the number of clusters to be constructed. Okay, so for k-means, we need also the number of clusters. Okay, so after the input, and then we go for step one. Step one, we construct a similarity graph G. Okay, as we said before, we have 3 different ways to construct the similarity between any 2 vertices. Okay, so after we construct the similarity graph, we can compute the Laplacian matrix L. Okay, L is D minus W. Okay, and then by using any software which can calculate eigenvector and eigenvalues, we can get the k eigenvectors correspond to k smallest eigenvalues. Doesn't have to be eigenvalue 0, but we choose k smallest eigenvalues, and k is given. Okay, given in the input. All right. Step 4, we construct the matrix E, okay, by using these k eigenvectors as their columns. Okay, and from E we can get y vectors, y1 to yn. All right. After we get the vectors y, we can cluster the points y1. Not sorry, this shouldn't be k, it should be n. Okay, we can cluster points y1 to yn by using k-means or k-medoid algorithm into clusters c1 to ck. Okay, to make sure that in each cluster ci, the corresponding points yji, they are close enough. Okay, or there are similar yi's being put in the same cluster. Okay. All right. So the output would be the clusters A1, AK. Okay, and for each A, let's say AI consists of Vj, where Yi is in Ci, is in cluster Ci. Hey guys, I'll give you, let's say, 2 minutes to have a look at this algorithm, and we also take some questions. Like question 1: how do we choose a appropriate value for k? We have emphasized this last week, where we have different ways to estimate k. For example, we talked about the bottom-up hierarchical clustering, which is the WARD algorithm last week. Even though in the WARD algorithm k is given, but you can sort of combine the WARD algorithm with entropy. Okay, the entropy of the clustering results, or entropy of the partition. Okay, and then if the entropy stopped decreasing, and then you can estimate that yes, this at this iteration, and K is appropriate number of clusters. Actually, there are many different ways to estimate K. Okay, but for the algorithms that we introduced here, we assume K is a known input or a given input. Okay, or you can also design your own algorithm to estimate K. Like if you combine entropy in your algorithm, okay, it could combine. You could combine entropy with k-means or k-medoid or what, or yeah, different ways to estimate K. What would be the cost here? Sorry, I don't get it. What do you mean cost and here? Is here the spectral clustering algorithm? I'm guessing computational cost, like the cost. Ah, you mean the computational complexity? Okay. That's a very good point. We actually didn't analyze or give an analyze of the spectral clustering here. I would say the computational complexity is actually similar. No. Yeah, so because in step 6, we do have a k-means algorithm here, okay? And in step 3, we need to find out all of the k smallest eigenvectors. So it would take some time here. Okay, at oops, I should point out at a step 3. Okay, so you can see that the spectral clustering from computational complexity perspective is more expensive. It's more expensive than k-means. Matrix redundancy last That's at least related to finding the eigenvalues. Yeah. Okay. So we didn't give the analysis of spectral clustering here. Alex, are you here? Would you mind to recommend some reading material to students about the cost or the computational complexity of spectral clustering? Alex, are you still here?
Yes, yeah, I am. Sorry, it took me time to find the button for unmuting. Yeah, I'll post a very nice paper that contains, I think it's referred in these slides at the very end.
Oh, yes, sorry. Yes, we do have it.
Yeah, it has detailed. Of course, it's more expensive than k-means clustering because it involves k-mean clustering, right? So the cost is given by the eigendecomposition, but for all of these matrix algorithms, we have efficient algorithms even for rather large problems. And the main benefit, of course, here is that the spectral clustering can also uncover the non-center based clusters. So in this sense, it's kind of algorithm of choice. Yeah, I'll put this paper. It's available on the web, so if you just click on the link, you will get the paper, and it's an excellent paper that gives all the details.
sorry, we couldn't analyze the cost or complexity here, but please, if you're interested, please take a look at the attached paper in the end of this.
Yeah, there it is on the very bottom.
Yeah. That's very good. That's very good. Yeah. You're interested in the cost. Okay. Where am I? Okay, here. Right. So we talked about spectral clustering algorithm, and now let's move on to the relationship between spectral clustering and graph partitioning. Okay. All right. This. Okay, so we've talked about min cards before, right? Okay, so the min card problem, for the min card problem, okay, let's take a look at the first point. Okay. For a given number k of subsets, the min card approach for graph partitioning simply consists in choosing the partition A1 to AK, which minimize this expression. Okay, so we talk about the definition of WAB given here. Okay, so suppose we have two sets A and B, and then WAB gives us the sum of the weights on the edges linking set A and linking the nodes in set A and set B. Okay. Right, so by using this definition, we can easily understand the min card approach for graph partitioning given here. All right, so we try to find out a partition A1 to AK such that the sum of the card, if we call WAB as the card of the card AB, okay, so the min card approach is to minimize the sum of the card between A and A complement. Okay, so for each component, for each partition, okay, so for each partition AI, we minimize, we couldn't say for each, but the sum, okay, the sum of the cards, A and A complement, okay, and we see that if K is equal to 2, and this min card approach becomes the standard min card problem. Okay, we split the nodes in a graph into two parts. Okay, and find out the edges with the min card on the edges. Okay, and separate the graph into two. Okay, so this is about min card for graph partitioning. Right. So notice that unfortunately minimizing T is not good. Actually, this is 2. Okay, minimizing this expression is not a good idea because if we minimize equation 2 directly, it will often produce clusters that some of the clusters contain only a single vertex or just a few vertices. Okay, why? Because in this expression, it doesn't consider the size of component AI. It doesn't consider component size. Okay, so to get rid of or to avoid this problem, we will minimize this expression. Okay, instead of minimizing the sum of WAI and AI complement, we will sort of normalize the cut of AI and AI complement by the size of AI. Okay, so we consider the size of AI. Okay, and we call this as a ratio cut. Okay, put the ratio here. Okay, now, okay, if we put the ratio, we will see that the ratio cut approach will find the clusters. We'll find clusters AI which have a reasonably large number of points, rather than just a few, because it normalizes or regularize cluster size to some extent. Okay. Now, for every partition, okay, for every partition A1 to AK, we can define the corresponding set of orthogonal indicator vectors Hj. Okay, and Hj is defined as H1j, H2j till Hnj by setting. So for each coordinate Hij, okay, Hij, if Vi is in the cluster Aj, and then Hij is equal to 1 divided by the square root of size Aj. If Vj is not in cluster Aj, and the Hij is 0. Okay. So we define this as orthogonal indicator vector Hj. Okay, and we can easily get that the length of Hj is 1. Okay, the length of Hj is 1. Okay, and for any two orthonormal indicator vectors Hm and Hl, if m is not equal to L, and then Hm and Hl, they are orthogonal. Okay, or the scalar product is equal to 0. Okay, because we see clusters Aj's are pairized disjoint. Okay. Now let's move on to talk about the relationship between graph partition and spectral clustering. Okay. Now we will have a look at these product. Hj transpose times L times Hj. Okay, according to the definition of Laplacian matrix L, okay, and the previous theorem, we can get this is equal to this expression, right? Okay, and as we see, according to the definition of Hij, okay, if I is in Aj and then it is non-zero, otherwise Hij is 0. Okay, so we can rewrite this expression by using Aj. Okay, J corresponding to Hj here. Okay, so we can rewrite this as this expression, the second equation. Okay, so we can rewrite it as sigma m in Aj and L not in Aj. Okay, so m in Aj and an L not in Aj, because if m is in Aj and L is also in Aj, and then you'll see that HMJ and HLJ, both of them are equal to this, 1 divided by the square root of Aj, right? And then it will be 0. So this part would be 0, right? So we consider, oops, oh, what am I doing? So we consider M in Aj and L not in Aj. Okay. And because you see the summand is for both M and L. So if we consider M in Aj, L not in Aj, and we will get also L in Aj and M not in Aj. All right. Okay. Now, according to the definition of Hij, because let's take a look at this HLJ, because L is not in Aj. Okay. VL is not in second one. VL is not in Aj. So HLJ is equal to 0, right? So this is equal to 0. And because M is in Aj, so HMJ is equal to 1 divided by square root of Aj. Okay, square root of Aj. Okay, and similarly for this part. Okay, similarly for this one. So now you can tell me what is the value for HMJ. So HMJ is equal to, guys, yes, it is 0 because M is not in Aj. And for HLJ is 1 divided by the square root of Aj, right? Because L is in Aj. Wonderful. Okay, so yeah, we will get these equation, right? Okay, so take a look at, now take a look at this. Okay, so this is exactly the cut of Aj and Aj complement, right? So one is in Aj, the other is not in Aj, right? Divided by the length of Aj. Sorry, because there is a square here, so the square root will be cancelled. Okay, so we get the length of Aj. Okay, so we see if we define the orthonormal indicator vector in this way, okay, we can perfectly gauge Hj transpose LHJ is equal to the objective function for ratio cut. right, for ratio card. Okay. Now, if we define edge, matrix edge, okay, be the matrix, let H be the matrix of size n times k with vectors hj, j from 1 to k as the columns of H. Okay, and then we can get this result. Actually, can easily prove it because as you see here, this is exactly okay, Hj transpose LHj, right? Okay, and if we sum up j from 1 to k, we will get exactly the trace of H transpose LH. Okay, guys, you can easily prove this. Okay, so we get our result here. The ratio card is equal to the trace of H transpose LH. Okay, and then we can conclude that minimize the ratio card. To minimize the ratio card, we have to find the disjoint sets A1 to AK, which minimize the trace of H transpose LH. Okay, and H is defined as by using the clusters AJ, J from 1 to K. Okay, so this is the relationship between spectral clustering and graph partition by using ratio card, this approach. Right? Okay, so to minimize the ratio card is NP hard. Okay, but take a look at the highlighted red part. Okay, so the Rayleigh-Ritz theorem from linear algebra tells us that such matrix H is obtained as the matrix with k eigenvectors corresponding to the k smallest eigenvalues of L as the k columns of H. Okay, so by using spectral clustering, we can also deal with the graph partition problem. Okay. All right, we are close to the end of spectral clustering. Okay, so let's take a look at a few more points. First one, just as before, these eigenvectors might be approximation of a linear combination of the indicator function 1aj. Okay, just approximations. So again, we cluster the n rows of H, okay, n rows of H into k clusters, C1 to CK, to obtain the partition A1 to AK. Okay. All right, after we get the partition, or for each partition, Vj in, if Vj is in the partition Am, if and only if the jth row of H belong to the cluster Cm. Okay, so we just use the spectral clustering in graph partition or in graph partitioning. Okay, so this is precisely what our spectrum clustering does. Okay, and besides the original heuristics with the connected components, we now see that the spectral clustering algorithm finds an approximate solution to the problem of finding A1 to AK, which minimizes the ratio card. Okay, the ratio card. in graph partitioning. Okay, so instead of in real applications, instead of using ratio card, we actually often use n card. Okay, in the ratio card, we see the ratio is the size of AJ. Okay, so the size of AJ would be the number of nodes in cluster AJ. Okay, so in NCAD approach, rather than use the size, we use the volume of AJ. Okay, so as we defined before, the volume of A is the sum of the degrees of nodes in A. Okay, the sum of degrees. So this is the difference between NCAD and the ratio card. And in real applications, we often use the NCAD. Okay, because yeah, real applications tell us that if we use the volume of AJ, we will get normally we will get better clustering results. Okay, and guys, again, you can refer to these material for the detailed proof of some of the theorems. Okay, so this is about spectral clustering and its relationship with graph partitioning. Okay, guys, do you have any question? Okay, let's have a short break for 5 minutes. We will come back at 5:38, and then we will talk about recommender system. Have a break. Okay, guys, can you hear me? Perfect, thank you. Okay, let's move on to talk about recommender systems. Okay. Recommender systems have been used for years and in different systems. Let's take a look at a few examples like Netflix. Okay. If you're using Netflix and the recommender system would like to recommend to you which movie you want to see next. Okay. And if you're using Amazon, Amazon would like to recommend you which book you can buy or you may buy next time. Or if you're using Kogan, anyone use Kogan here? For my curiosity, Kogan, anyone use this? Oh, okay. Anyway, I use this. Okay, so Kogan would recommend which gizmo to buy next. I used to have a rice cooker made made by Kogan. Nice, Simon. Okay. And if you're reading paper from IEEE's Explore, and then IEEE Explore would like to recommend which articles might be of interest to you, given what article you have just read, or you have just searched through IEEE Explore. Okay. For recommender systems, there are two major kinds of recommender systems. One is content-based, the other is collaborative filtering. So content-based is based on the item's intrinsic similarity. Okay, intrinsic similarity. For example, including, let's say, similar properties, qualities, kind, etc. For example, a book might be recommended because you bought a book on a similar topic. Okay, so content-based is based on the intrinsic similarity of items. Okay, it doesn't include users, okay, or the property of users. Okay, just based on the intrinsic similarity of items. But collaborative filtering is based on, so the items are recommended based on some similarity measures between users and items, okay, based on the ratings of items by the community of users, okay, like the ratings of movies that you watched. Okay. So for content-based recommender system, it often suffers a serious problem because, as we say, it is based on the intrinsic similarity of the items. Okay, but the intrinsic similarity are often denoted by humans. Okay, and humans, the notations are often, the content is often semantic notations. Like if you buy a jacket or a pair of shoes on eBay, some people like the jacket or shoes very much and they give very high ratings to the items. But some people, they have different semantics and they give different ranks. So it is very hard for machine to deal with semantics. Okay, so this is the problem of content-based recommender system. For collaborative filtering, it tends to be superior in performance and doesn't rely on human advice, okay, or semantic notation, right? So a representative example of collaborative filtering. So here, assuming users are rating movies that they have seen. Okay, on the basis of such information, we would like to recommend to a user a movie that this user has not already seen. Okay, so for collaborative filtering, there are two main approaches. The first one is called neighborhood method. Okay, today we will talk about neighborhood method, and the second is latent factor method. Okay, so neighborhood method, if you take a look at the keyword neighborhood, you may say that maybe we need to calculate the distance between the items or the similarity between the items. Okay, it could be items or users. Okay, now the neighborhood method comes in two flavors. Okay, the first is based on the similarity of users, okay, which I highlighted here in blue. Okay, let's take a look at the similarity of users. So if two users are similar users, okay, and then it happens that the two users gave similar evaluations to movies that they have both seen, right? If the two users are similar users, and then they often give similar evaluations to movies that they have both seen, right? And now, if there is a movie which one of the users liked a lot, but the other user hasn't seen, okay, and then in this case, it is reasonable to recommend such a movie to the user who hasn't seen, right? So this is based on similarity of users. The second flavor is based on the similarity of items, which are highlighted in green here. Okay, so if two items are similar items, and then let's say that the items are movies. Okay, so it happens that the two movies receive similar ratings by most users, right? If two movies are similar, and then often they will receive similar ratings by most users. Okay, and then if a user hasn't seen one of the two movies, oops, my mistake. If a user has seen one of the two movies and liked it, okay, and then it is reasonable to recommend the other movie to this user, right? So this is based on similarity of items. All right. So note that in both approaches, movies, okay, either based on similarity of users or based on similarity of items. Both approaches, in both approaches, movies are not categorized and compared by their intrinsic features. What we use are based on the ratings of movies given by the users who watched the movies, right? So we do not rely on intrinsic features of items. What we rely on the wisdom of the crowd. Okay. Now we talk about the similarity of users and the similarity of items. So how do we measure the similarity of users and items? Okay. So we can construct a sparsely populated table of ratings R. Okay, pay attention here. So the rows in matrix R will correspond to movies. The rows correspond to movies. The columns are users. Okay, so I draw a matrix here. This is matrix R. Okay, rows are movies. So M1 ... MJ ... and columns are users. So user 1 ... user I. Okay. Right. And the entry RJI of the table, if the entry is non-empty, okay, which means the rating user UI gave to movie MJ. Okay, so the entry RJI represent the rating that the user UI gave to movie MJ. All right, so this is the first step to construct a rating table or rating matrix R. Okay, and normally such a rating is a number of stars. Could be range from 1 to 5 or 0 to 5 or 0 to 10. Okay, or whatever the range is. Okay, so the ratings are normally number of stars. Okay, so to measure the similarity of users and items, first we need to regulate all positive ratings. Okay, so the first thing we need to regulate all positive ratings, because as we say, ratings are number of stars. Let's say in range 1 to 5. Okay, those are all positive numbers. Okay, so having scores or ratings which are all positive numbers is not very convenient. Okay, because from the number itself, we don't know, let's say, the average rating to an item. Okay, and we don't know whether, let's say, a score 4 is above the average or below the average. So we couldn't tell from the scores if the score are all positive numbers. Okay, so the first thing we need to do is to regulate all positive ratings. Okay, so how do we regulate all positive ratings? Is we compute the mean rating, R bar of all ratings of all users for all movies. Okay, so you can take a look at the expression here. Okay, so R, the mean R is defined as this. So this is the number of users, this is the number of movies. Okay, and this is the sum of all the ratings. Okay, so after we get the mean, R bar, we now obtain from the table R a new table R bar. Okay, by replacing all ratings RJI in table R by the value R star JI, which is equal to RJI minus the mean R bar. Okay, so now the numbers R star are already more informative. Okay, because if R star JI is positive or is greater than 1, it means that this user, the user UI, has liked the movie MJ above the average. Okay, so R star JI is more informative. Okay, so this is the first is to regulate all positive ratings. The second is to remove systematic biases by users and items. So what is the systematic bias by users? Okay, so take a look at this point. Some users, so users are highlighted in blue. Some users are more generous and tend to give high scores than the average user. And some users are more critical and tend to give lower scores than the average user. Okay, but for recommender system, we are not interested in evaluating the generosity of users. We want to assess only the test of users, which means what they like more and what they like less. Okay, so this is the systematic bias by users. And similarly, the systematic bias by items. okay, which I highlight in pink. So similarly for movies, okay, for movies, some movies get high scores because they're popular at the moment, okay, and some movies have less hype about them because they might be older and less trendy. Okay, again, for recommender system, we are not interested in absolute popularity or trendiness of a movie. Rather, we would like to assess how intrinsically likable a movie is. Okay, so these are about the systematic biases by users and items. All right, now, how do we remove those biases? Okay, so we want to remove the systematic biases of both the users and movies. How do we remove? Okay, here. For that purpose, we introduce for every user UI a variable VI. Okay, for every user UI a variable VI standing for the individual bias of user UI. Okay, reflecting his tendency to give overall higher or lower scores. Okay, and similarly for every movie, MJ, we introduce a variable μJ, standing for the hyperbias of movie MJ. All right, to remove these biases, we try to minimize the following expression. Okay, we minimize S, V, and U. Okay, so SVU is defined as the sum of the residual. Okay, so what is the residual? The residual is defined as R star JI. Okay, so R star JI we have defined it before, which is RJI minus the average, the mean. Okay, so RJI minus the bias of user I, the bias of user I, and the bias of item J. Right? So this is this gives us the residual. Okay. So the problem is to minimize the residual, minimize the impact from the biases of users and items. Okay. And notice that, so for items, the variables mu's are constant shifts of rows. Why is that? Okay, so mu's are constant shifts of rows, and v's, the variable v's, are constant shifts of columns. Okay, why is that? Because take a look at this expression in the brackets. Okay, so for each item mu j, so this residual is independent of user I. Okay, so we can get what I wrote here, R star ji minus mu j for any user I. Okay, so that's why we have this result that mu's are constant shifts of rows. Okay, and similarly we have, sorry, this is too small. Yeah. So for variable v's, there are constant shifts of columns because we see the expression I wrote it here. Okay, it is also given from the residual. Okay, so for every vi, okay, we have R star ji minus vi. Okay, so for this vi, this residual is independent of item J. Okay, so that's why we say these are constant shifts of columns. Okay. Right. So if we can find appropriate VIs and mu J's, and then we can get the residual R tilde Ji, which is equal to R star Ji minus the bias of user and bias of item. So this residual can better represent the intrinsic semantic of a user UI for our item MJ. Okay. And to solve this problem, because this is a least square problem, and it can be easily reducible to a system of linear equations. For example, we can use a gradient descent algorithm to easily calculate. Yeah, thanks. Okay. Yeah, so by using, for example, gradient descent, we can easily get the solutions for V and U. Okay, guys, we will stop here. And Thursday, we will move on to talk about neighborhood-based method. Thank you. Thanks. Thank you, guys, for your attention. Thank you. I'll see you on Wednesday.